In 2005, NASA's Cassini spacecraft was conducting a routine flyby of Saturn's moon Enceladus, and its instruments detected something impossible: water vapor. Active geysers of water ice and gas, shooting from the south pole of a moon that, by every physical model we had, should have been a frozen, dead rock. Cassini flew directly through that plume, and what it found changed the search for life in the universe. A liquid water ocean, active hydrothermal vents, complex organic molecules, the building blocks of life, on a moon 500 kilometers wide, smaller than the United Kingdom. In this video, I'm going to show you exactly what Cassini found, why it should not be there, and what it means for one of the biggest questions in science. Enceladus is 504 kilometers wide. Its surface reflects 99% of the sunlight that hits it, making it one of the coldest objects in the solar system. By every model we had, it should have been dead. The south pole of Enceladus has 4 parallel fractures in its icy crust, each running for approximately 130 kilometers. Scientists call them tiger stripes. From these 4 fractures, Enceladus is continuously venting water vapor, nitrogen, carbon dioxide, methane, and complex organic compounds into space. The geysers reach heights of 400 kilometers. Some of the ejected material escapes Enceladus entirely and becomes part of Saturn's E-ring. The moon is literally feeding one of Saturn's rings. For Enceladus to do this, it needs an internal heat source. For a body its size, the candidates are very few. The leading explanation: tidal heating. As Enceladus orbits Saturn, the gravitational pull of Saturn and the other moons flexes and kneads its interior, like a squeezed rubber ball. That mechanical energy converts to heat. Enough heat to maintain a liquid water ocean beneath roughly 30 to 40 kilometers of ice, on a moon with no business having any heat at all. Between 2005 and 2017, Cassini made 23 close flybys of Enceladus. On several of those flybys, it flew directly through the active plume, essentially tasting it. This is what Cassini's mass spectrometer found: water, carbon dioxide, methane, molecular hydrogen, ammonia, silica particles, and complex organic molecules with molecular weights over 200 atomic mass units. That last one deserves a moment. Complex organic molecules, carbon-based compounds of significant complexity. In 2018, scientists identified aromatic compounds in the plume material, ring-shaped carbon molecules, the same types of molecules that are precursors to amino acids, to the building blocks of proteins, to the building blocks of life. And molecular hydrogen, this matters enormously. On Earth, at hydrothermal vents at the bottom of the ocean, microorganisms survive by reacting hydrogen with carbon dioxide to produce methane and energy. This process is called methanogenesis. The hydrogen to carbon dioxide ratio in Enceladus's plume is exactly consistent with what you would expect if this process were happening in the ocean below. The silica particles Cassini found deserve special attention. Silica nanoparticles form under very specific conditions, when water above 90 degrees Celsius encounters lower temperatures, and the silica precipitates out of solution. On Earth, this happens at hydrothermal vents. The only way to explain silica nanoparticles in the Enceladus plume is if hot, silica-rich water is reaching the ocean and being vented to the surface, which means Enceladus has hydrothermal vents on its ocean floor, under 30 to 40 kilometers of ice. On Earth, hydrothermal vents host some of the most isolated ecosystems on the planet, species that live in complete darkness. No sunlight, no photosynthesis. surviving entirely on chemical energy from the vents. These ecosystems were discovered in 1977, and they fundamentally changed our understanding of what conditions life requires. Enceladus appears to have the same conditions: a liquid water ocean, a rocky seafloor, hydrothermal vents providing chemical energy, complex organic molecules as raw material. It has had these conditions for potentially billions of years. In 2018, Cassini made its final pass. The spacecraft was running low on fuel. Rather than risk an uncontrolled crash, contaminating a potentially inhabited world, NASA sent Cassini directly into Saturn's atmosphere. It burned up on September 15, 2017, transmitting data until the moment contact was lost. In its final months, Cassini made its deepest dive through the Enceladus plume, and the data it returned was the most compelling of the entire mission. Molecular hydrogen was present in concentrations that can only be explained by ongoing chemical reactions between hot water and rock, specifically the reaction called serpentinization. On Earth, serpentinization produces environments that some scientists believe may be where life itself first emerged. Not at the surface, not near sunlight, deep underwater, in chemical reactions between rock and water. Enceladus has those same reactions happening right now, in real time, at this moment. Here is what makes Enceladus genuinely unsettling. Not scary in the way Neptune's winds are scary. Unsettling in a much deeper way. If life exists on Enceladus, in an ocean that has never seen sunlight, under 30 kilometers of ice, heated only by tidal forces, sustained entirely by chemistry, then the conditions for life are so broad, so tolerant, that life may be extraordinarily common in the universe. There are at least 6 other moons in our solar system that may have subsurface oceans: Europa, Ganymede, Callisto, Titan, Triton, Nemes. If even one of these has life, then the galaxy, with its 400 billion stars, could be filled with microbial life. And that is terrifying, not because of what it means for us, but because of what it implies about the Fermi paradox. The question of why, if life is so common, we have heard nothing from anyone else. Either life is common and almost never evolves beyond microbes, or intelligence is rare and we are extraordinarily alone. Or something happens to intelligent life before it becomes spacefaring, and it happens consistently. NASA's answer to Enceladus launched in October 2024, Europa Clipper, a spacecraft designed specifically to investigate Jupiter's moon, Europa, which also has a subsurface ocean, arriving at Jupiter in 2030. It will make 50 flyby passes of Europa. Its instruments include a mass spectrometer almost identical to Cassini's. If Europa's plumes contain the same chemical signatures as Enceladus, we will have 2 independent data points, 2 separate oceans, 2 separate sets of conditions, both potentially habitable, in the same solar system, around the same star. The statistical implications of that are difficult to overstate. Enceladus is 500 kilometers wide, smaller than the United Kingdom, and it may be the most important object in the solar system, not because of what we know about it, because of what we don't. Cassini is gone. Europa Clipper is on its way, and somewhere under 30 kilometers of ice on a tiny frozen moon, something may be alive right now, completely unaware that we exist. The next moon in this series has an ocean too. But what makes it different and more dangerous is what scientists found in its ocean that they didn't expect. And if this video genuinely unsettled you in the best possible way, subscribe to Untold Universe, Tuesday, Thursday, Saturday, every week.